today's class, we will try to understand the plasma behavior by considering it as a fluid. So, it is plasma as a fluid. So far in our discussions, we have taken plasma to be a particle and we have used the Lorentz force basically to obtain the trajectory of a particle when it experiences different types of electric and magnetic fields. But most of the times plasma can be treated as a fluid which is made up of two independent or interpenetrating fluid. One is called as an electron fluid and another is an ion fluid. So, this model of plasma in which you consider the entire plasma to be made up of two interpenetrating fluids is called as the two fluid theory. Now, what we are going to do in today's class, we will try to write down the complete set of equations which are required to understand plasma as a fluid. So, in our earlier discussions, we have seen how individual equations describing the fluid motion can be derived. We are going to establish the complete framework of governing equations. So, if you remember, our equation was very simple when you are considering plasma to be a fluid, to be a particle. This is something like this. So, it is m dV by dt is equals to the force due to the electric field plus the force due to the magnetic field, right. So, when you solve this equation, depending on the type of field that we have taken, we will get the position as a function of time. So, this is what our approach has been so far. Now, more importantly, plasma most of the times can be easily explained by considering it as a fluid, right. Now, how do we make the change? So, let us say we start from the basic equation. So, we will say F, if it is made up of n number of particles, F is summation of Q, summation over I, Q times E plus Vi cross B, right, where we can use the mean velocity. In this, we can use what is called as the mean velocity as V is equals to sum over Vi divided by delta n, where delta n is the total number of particles. Now, as long as you are considering plasma as a particle, you are addressing the individual behavior of the particle. But when you consider it to be a fluid, you no longer are looking at the individual behavior, rather you are looking at the collective behavior of the entire fluid and trying to understand or try to write equations pertaining to the motion of the fluid. So, where delta n is the total number of particles in this Lorentz force equation, which gives us the velocity v. So, if you consider the number of particles per unit volume, then you can write delta n by delta v. This is the total number of particles and the number of particles per unit volume is this. Now, you can write this, the Lorentz force expression, using this as Q delta n times E plus Vi cross B, right. So, this is the electromagnetic force that the plasma will experience, and if you want to use the expression, the number of particles per unit volume, you have to write n delta V times Q times E plus V cross B. Or the electromagnetic force the particle or the plasma experiences per unit volume is equals to NQ E plus V cross B. Right. So, this quantity that appears on the left hand side is called as the force density. We are just writing equations in a different notation, right. So, this is called as the force density, or which is also equal to force per unit volume. Now, so far we have been addressing the force just by this, right, on the particle, but we are now calling it or quantifying it as force per unit volume. The reason is we are not considering the individual particle, rather we are considering the volume of the fluid, because we are referring to the entire volume of the fluid. We want to see how much is the force that is experienced by a unit volume. So, similarly we can also write the momentum. Momentum P is equals to summation over I m ui. You say mass is same for all the particles. It can be written as m delta n v or m n delta v. Right. So, this is now the momentum, this is the total momentum. So, total momentum is equals to m n delta v v cap. Momentum density, similar to the force density, we can write the momentum density is equals to momentum divided by the volume, which is equals to m n v. Right. So, now we have force density and momentum density. So, both of these can be used while using the plasma, while using the fluid equations. So, in addition to the electromagnetic force, when plasma is considered as a fluid, it also experiences two additional forces, which are called as the pressure force and viscous force. So, these two forces are in addition to electromagnetic force. As long as we have considered plasma as a particle, we do not have to deal with this type of additional forces, because it is only the particle, right. But when you consider a fluid, we know very well that differences of pressure at different points inside the fluid can exert a force which is called as the pressure gradient force or pressure force, and the relative movement of fluid layers with respect to one another are influenced by what is called as the viscous force, right. So, if you just want to establish an expression for this, it is like, so if you have a neutral gas, constituent of neutral gas molecules will exchange momentum when they collide, right. Now, this momentum is what leads to the idea of pressure, or the rate of momentum transfer to the walls of the container builds up the pressure or the force that is experienced by unit surface area on the walls is the pressure, right. Now, the momentum that is lost when these particles collide with each other will be proportional to the relative velocity of the particles before the collision and after the collision. So, we can write the F is proportional to U minus U naught, and if you bring in tau to be the mean free time between the collisions, then we can write tau is mean free time. Then we can write F is proportional to 1 by tau. So, in total we can write F is equals to Nm u minus u naught divided by tau. So, this rate of change of momentum is basically the force. Now, this can be added to the force equation that we had written earlier, right. So, we can write Mn dou u by dou t plus u dot del dot u is equals to Qn E plus V cross B minus Mn nu u minus u naught. Nu is coming from the inverse of the tau minus del p, right. So, this is the equation which is valid for the fluids. So, this is the term which takes care of the electromagnetic force. This is the term which takes care of the viscous force, and this is the pressure force. And whatever that appears in the square bracket, as we have already discussed, this is the total derivative. So, if you look at this equation, on the left hand side you have the rate of change of momentum, on the left hand side you have the acceleration term, but written by using a total derivative, because we want to account for the motion of the fluid also while following the motion. So, the acceleration of the fluid element or fluid volume is equals to the effects of imposed by the electromagnetic force, the viscous force and the pressure force. So, if you take this, we can now go ahead and see how will be the full set of equations that will appear when we consider plasma as a fluid, right. So, now plasma is going to be called as a mixture of two interpenetrating fluids, For simplicity, we will consider the plasma to be fully ionized, and that means that there are only electrons and ions and no neutral species are present. Then we consider plasma to be isotropic. So, that means that the plasma density is same in all directions. So, we can say for simplicity that there will not be pressure gradients in the plasma, and we consider plasma to be collisionless. So, what does it mean? It means that we do not have to worry about the collision term. Collision term can be neglected, right. So, when we want to establish the complete set of governing equations for plasma as a fluid, we need to make these assumptions. Now, what are the intuitively we can make a guess how many equations or what are the equations that we want to involve. Let us say we want to conserve mass, we have to conserve mass when the fluid moves from one place to another place. We have to conserve momentum right? And then we will need the ideal gas equation, and then since plasma is electrodynamic in nature, plasma as a fluid also can be influenced by the electromagnetic forces, electromagnetic fields. So, it is invariant that we have to bring in the Maxwell equations. So, we have already discussed what is the need for considering plasma as a fluid. So, just to have a repetition. So, plasma, when it is considered as a particle, we always thought this type of fields, let us try this type of different electric and magnetic fields and then try to understand the plasma motion. But at the end we realize that generally the fields that we try to impose are not prescribed. So, we do not prescribe what type of fields will exist, but they are actually determined. So, plasma itself determines what kind of fields will be there, and it is a self consistent motion. So, particle theory may not actually be suitable for all for the entire description of plasma, right. So, this is the set of equations that we need. Okay. So, let us say we write these conservation laws and equations mathematically. So, let us say we assume the charge density of plasma as rho is equals to Ni Qi plus Ne Qe. What is this? This is the charge density. Since plasma is neutral, the total charge density that is available in the plasma is rho is equals to Ni Qi plus Ne Qe. Let us say we call this equation as 1. Since it is moving, there are currents inside. The current density, let us say we call this as J, which is equals to Ni Qi Vi plus Ne Qe Ve. N is the number of particles per unit volume, Qi is the cumulative charge of ions, Vi is the velocity of ions, plus Ne Qe Ve, same terms for the electrons. Okay. So, these are two equations. Then we will need the momentum equations. Right. So, we will write Me Ne dou Ue by dou T plus Ue dot del times Ue is equals to minus del Pe plus Qe Ne E plus Ue cross P. What is this? This is the momentum equation for an electron, which is the left hand side you have the rate of change of velocity, and on the right hand side you have all the forces which are responsible for this rate of change of velocity. Then we have to write a similar equation for an ion. So, we will write Mi Ni dou Ui by dou T plus Ui dot del times Ui, the advection term, is equals to minus del Pi, the pressure force, plus Qi Ni E plus Ui cross P. Let us say we call this equation as equation number 3, this as equation number 4. Now, these are the momentum equations, right, for electron and ion. Then we have to write the Maxwell equations. Maxwell equations tell you how the charge densities and the fields and the currents are connected with each other. So, Maxwell equations are del cross E is equals to minus dou B by dou T del cross del dot B is equals to 0 and 1 by mu naught del cross B is equals to Ni Qi Ui plus Ne Qe Ue plus epsilon naught dou E by dou T. And what else you have? You have one more equation which is del dot E, the divergence of the electric field, is equals to del dot E by epsilon naught epsilon naught times del dot E is equals to Ni Qi plus Ne Qe. Let us say we call this equation as equation number 5, 6, 7 and 8. So, we have 4 Maxwell equations. I have just written them here. Okay. Then what else? You have to write the equation pertaining to the conservation of mass, which is the continuity equation. So, we have to write the continuity equation for the electron fluid as well as for the ion fluid. The continuity equation, which is dou Ne by dou T plus del dot Ne Ue is equals to 0. Call this equation as equation number 9. Dou Ni by dou T plus del dot Ni Ui is equals to 0. We call this as equation number 10. We already have 10 equations. In addition, we will need the thermodynamic properties to be considered, or the kinetic properties of the fluid, which is just a fluid, kinetic properties, which can be addressed by the simple equation P is equals to nkt. So, electron fluid's pressure is equals to Kb, electron temperature, and Ne. Or Pi is equals to Kb Ti Ni. Let us say this is equation number 11, equation number 12. They can also be written as Pi is equals to C rho I to the power of gamma, or Pe is equals to C times rho E to the power of gamma. C is a constant and gamma is the ratio of specific heats. All right. So, let us say we call them as equation number 13 and 14. Right. So, we now have 14 equations. Right. So, now let us see if we want to solve them, what is the basic approach. So, basic approach is you can solve them, you can obtain few variables, you can substitute those variables into other equations and then obtain those unknown variables. So, ideally we will expect that we will need a condition to be satisfied always when you are solving some equation. So, we will always read. So, number of variables must always be equal to the number of equations, or we are more familiar to call this as unknowns. Number of unknowns should always be equal to the number of equations. Now, let us try to count how many equations we have and how many variables do we have. So, we have how many vector variables. So, you have the velocity UE will have 3 component velocity, UI will also have 3 component velocity. Let us say x component, y component, z component, x component, y component, z component. The electric field will have Ex, Ey, Ez. The magnetic field will also have Bx, By, Bz. Right. So, the number of variables, so these are the vector unknowns. We are calling them as the vector unknowns. So, we will say vector unknowns are the electron fluid velocity, the ion fluid velocity, the electric field and the magnetic field. Similarly, we have scalar unknowns. What are they? We have Ne, Ni, Pe, Pi. So, equation numbers 3, 4, 5, 6 are vector equations. Right. And 7, 8, 9, 10, 11, 12, 13, 14. Yeah, equation 1 is a scalar equation. Let us say we write it here, it will be easy. This is a scalar equation. Since the velocity is there, this is a vector equation. This is a vector equation. This is a vector equation. These are basically vector equations, and here velocity is there. These are also vector equations. These are scalar equations, right? But in essence, we have these variables which are scalar and vectors. So, we have in total we have 16 unknowns, right. So, let us see how many we have. So, we have 3 component magnetic field, 3 component velocity, ion velocity, 3 component electron velocity and 3 component electric field, right. So, we have 12 variables from here, and then we have the pressure of electron, pressure of ion, number of electrons and number of ions, right. So, hence we have 16 unknowns in total, right. But how many equations do we have? 16 unknowns we have, and the number of equations. We have 2 continuity equations, right. We have momentum equations, so this is a vector equation which upon expanding can be written into 3 component form. So, we have 6 equations which are from the momentum equation. Then we have 4 Maxwell equations, then we have two ideal gas equations. Ideal gas equations. And within Maxwell equations, we have two scalar equations and two vector equations. Because you go here, yeah. So, all of these are not vector equations. This is not. So, in this there are two equations which have divergence. They are the scalar equations, and so this is the scalar equation, and this is a scalar equation. This is a vector equation, and this is a vector equation. So, two vector equations will, upon splitting, will give you 6 equations. This is equal to 6. This is plus 2. So, this is, so in total 2 for the continuity, 6 for the momentum, 8 for the Maxwell equations plus 2 for the ideal gas equation. So, we have 18 equations in total. Fine. So, this is just for the sake of remembering continuity, momentum, Maxwell, ideal gas, right. But in contrast, we see that there are only 16 unknowns. So, we have 2 extra equations, right, 2 extra equations. Let us see if there is any redundancy in the number of, in the equations that we have considered. The point is there any equation which is conveying the same message or same information as the other equation, right. So, we have to see if there are any 2 equations which are conveying the same message. In that case, we can drop one equation and we can bring this equality between the number of equations and the number of variables or the number of unknowns the same, right. Now, if you see this equation, del dot B is equals to 0, what it conveys is that the divergence of magnetic field is always 0, or it also says that there is no way that you can have magnetic monopoles. You take these 2 equations, these 2 Maxwell equations, we can establish a very interesting relation. So, del dot B is equals to 0, we know that, right. Now, let us say del dot, if I take a divergence of del dot del cross E, which will be equal to del dot minus dou B by dou T, right, or minus dou by dou T of del dot B, which is equals to 0, right. So, having this equation del cross E is equals to minus dou B by dou T, which is equation number 1, equation number 5, yeah, the first Maxwell equation that we have written. So, the idea is if you take a del dot, if you take a divergence of this, you are going to, using vector identities, we are going to establish that del dot B is equals to 0, because the divergence of curl is 0. You come back here. So, this, even if you know if you do not know this, you know that this is 0. So, del dot B has to be 0. So, equation number 5 is conveying the same message as equation number 7, equation number 6, right. So, in that case, we can keep only one Maxwell equation among these equation number 5 and 6. So, only one equation can be considered. That means, now we are in a situation, we have 16 unknowns and 17 equations. We have to get rid of one more equation. Now, if you go here, if you take this continuity equation, which is this. So, let us say you take the total number Ni plus Ne as n, and substitute Ni is equals to n minus Ne into into equation number 9, no, equation number 10. So, what we will get is dou n I will get is dou of n minus n e by dou t plus del dot n minus n e times u I is equals to 0. So, if you take the total number to be a constant, you will get the same equation, you will get equation number 9 from this, which means that out of the two continuity equations, we can only take one equation. So, that means one continuity equation can be dropped. So, in total we now have 16 equations which are matching with the 16 unknowns. Let us see what those 16 equations are, so that we can summarize this discussion, right. The 16 equations are, we will need this charge density and the current density. We will need the momentum equation for ions and electrons, and out of this we will probably take this equation and this equation. How many are there? 1, 2, 3, 4, 5, 6, 7, and these two equations are actually equivalent to 6 equations, right. 6, 8, 9, 10, 11 from here, and out of these we will take only one equation, and out of these two we will take one equation. That is it, right. So, in total we have the equal number of equations and equal number of variables. So, this describes the complete fluid system using these equations, right. So, this is what it is. We now have the complete set of governing equations which can describe the movement of fluid, which is the plasma. Movement of a fluid which is electrodynamic in nature. So, it demonstrates the properties of a fluid, and at the same time it also has an ability to be influenced by the electric and magnetic fields. Okay.